Let's begin. C3, real number and one-dimensional Euclidean vector. So we are very familiar with the number line that represent the Euclidean space, one-dimensional Euclidean space that is along a straight line. So if I introduce a number line, usually we choose a point as the origin. Let's see. The position of a particle in space is conveniently expressed in if we introduce a vector. We will extend this idea to the three-dimensional Euclidean space, and a vector is an algebraic manifestation of Euclidean space. Yes, right. So actually, the most fundamental vector is a displacement. We investigate the one-dimensional vector space. All right. Explain how to represent a point in one-dimensional Euclidean space with a dimensionless unit vector. Unit vector, there is a straight line, and any line segment is a parallel to this line. There are only two directions, either to the right or left. So if I want to find out a unit vector out of any possible vectors, some vectors is heading toward the right and another set is heading to the left. So anyway, if I choose this one, unit vector can be computed. Let me say it is A. A divided by the magnitude of A. Magnitude of A is just the length of A. So if I look at this one, in space, both of them are of dimensions of length. And because of the division, the length cancel, and the unit vector is always dimensionless. Okay? Whether it comes from a displacement, velocity, acceleration, force, electric field, gravitational field, in any case, unit vector is independent of any physical dimensions. Okay, so I can choose a unit vector that can be along this direction. Another choice can be to the left. So it is possible to choose unit vector along this direction, and another way is to choose E hat to the left. So only two possibilities. And they are linearly dependent. So if I multiply negative sign on it, then it flips to the other direction. So the choosing either to the right or left, choosing one of the two directions is just depends on your preference. Okay. As a result, any vector along a straight line connecting 2 points, suppose that we have A and B connecting 2 points, we have a unit vector and the ratio of these two vectors, the length divided by this unit length. So in that case, we have a real number, and actually this real number has the dimension of length. In the case, it is representing space. the physical definition of the real number can be applied to represent the point P along a straight line by making use of vector notation as this one. Okay, this is a point. This is a reference point. Let me replace this guy with the origin. And if I have some point P, then this is a distance. This distance is x multiplied by unit vector. But this is distance, and then this represents the direction. Okay. We remember this E is just a one direction. We have x-axis, so we can use E hat, either E hat or E1 hat. If I want to extend to 2 or 3 dimensions, it's better to attach the subscript 1 to represent it as denote this one as a unit vector along the x-axis. Okay, now I can represent a point on a straight line. This vector, this is a zero vector, it's an additive identity. Zero vector represents the origin. And if I know the x, that x represents the distance from the origin to that point. And as I told you, this E hat can either to the right or left. So as a result, x represents the translational operation. Translational operation. So from some point to another. This is called the displacement, changing the position of a particle. So this displacement is equivalent to the translation. Translation, it has a magnitude, but it keeps the direction. We call this one to be displacement vector. And that is the most fundamental vector. Explain the notation x and x that are conveniently used in physics. In physics, we use italic letter to represent a physical quantity. Any physical quantity, especially scalar. Scalar means it can be represented by a single real number. If I say a number that does not have to be equal to mathematical number, it may include dimensions of mass, length, and time, and their powers. Okay? Up to this unit, it becomes, if I separate this unit, then that physical quantity becomes a mathematical real number. All right. So single real number is enough to describe that physical quantity, then we say it is a scalar. If it is a physical quantity that both have its own magnitude and direction, then we say it is a vector, and it is denoted by bold italic letter. Italic letter, this is simply italic, and this is italic and bold. Sometimes I can attach an arrow on top of a italic letter. This is equivalent to, right, this is a bold-faced X. So you can, sometimes we can write in this manner. So, unit. Any physical quantity has its own physical dimensions. And if I pull out all of the physical dimensions into a single factor, then any other similar physical quantity, for example, 1 kilogram of mass and 10 kilogram of mass. We have two massive particles and we have a unit. If I pull out factor out this unit, physical unit that contains the physical dimensions, then we are left with pure mathematical number. This is a real number. So here C represents the mathematical real number, and this is called a unit. It can be kilogram or gram or ton or pound. So bold italic letter is to represent a vector, and vector has the magnitude and simultaneously it has its own direction. What are the dimensions in physics? Physical dimensions of quantity is defined by the availability of making an operation such as addition, subtraction with another physical quantity. Yes, right. We solved the problem in the previous class, 1 centimeter and 1 kilogram. Can we add them up? Impossible, impossible. Why? Because their physical dimensions do not match each other. So it is allowed to add two physical quantities only if the two physical dimensions are the same. It's fine. I can add 1 centimeter and 1 meter. That's fine. But although it is allowed, it is not neither 2 centimeter nor 2 meter. We should unify the dimensions, unify the unit. So it is a 1 centimeter plus 100 centimeter. So I have 101 centimeter. That's correct. So first of all, dimensions must match each other. Even if dimensions are the same, the unit should be unified to make a simple operation. Be careful. And when we factor out a unit, we have to count the dimensions of length, mass, and time, and they are arbitrary powers depending on quantity we are interested in. So we usually say these are called a base standard or base quantities. Explain the algebraic structure of one-dimensional vector space. Vector space is something like a set and whose element is a vector. And vector, I told you, the most fundamental vector is a displacement, changing the position from a point to another in three-dimensional space. But right now, we are interested in the one-dimensional space, one-dimensional Euclidean space along a straight line. So any point on a straight line can be represented by a real number with the dimensions of length along the unit vector. Okay, so we have origin and x and unit vector along that direction. That's fine. In that case, I can make an operation of a displacement. Addition of two displacements. You go to the right and then return to the same point, or go to the right 2 steps and return by 1 step. So the final displacement is this one, something like that. So I would say this is x, and this is another displacement y. These consecutive displacements result in the resultant displacement is a sum. And we know the answer is the same as y plus x. Why? Not because we learned in mathematics, but because we know. Go to the right by 2 steps, to the left 1 step, or 1 step first and then this. So this is x vector, y vector, and this y vector, x vector. Anyway, the final result is this one, and final result is this one from the start and end point. Start, this is the starting point and end point. So this one and this one, they are the same by experience. And in mathematicians generalize this idea to apply to number theory, and that they have constructed some algebra. So this one is this commutative law is not coming from mathematics, but comes from our experience. And we have constructed the mathematical model for this displacement. Okay? In a similar manner, we can extend this idea to add 3 vectors. What's that? You go, 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 or go, back, go, something like that. So any combination of ordered displacements results in the same value. So I can add these 3 vectors in many ways. I can add these 2 first, or I can add these 2 first. Either way, after that, I can find out the resultant vector by adding these 2 vectors. I can find the resultant vector by adding these 2 vectors. By experience, we can know about this. Even we can extend this one into 3-dimensional space. Why don't we represent this one x, y, and z? So way to start from this point to this vertex, there are many. For example, x, y, z, or x, z, y. Okay? Y, z, x. So there are so many ways, but after you add the 3 displacements up, the final result is just a diagonal connecting two opposite vertices. Okay, so this is what's easier to understand. Okay, so if you read the mathematics book, then they pretend they knew everything already, but it's a lie. Due to our own experience, we have constructed a model, and mathematical model is constructed. The first model is called Euclidean geometry. The distributive law, okay, we can multiply some scalar in front of a vector. Later, we will study some applications. For example, we have a displacement, and if I take the derivative or this change in the displacement, divide this one by time, what's that? This is a displacement divided by time. So that is velocity. Okay? And change in velocity, change in displacement divided by time. Time rate of changing position, right? In that case, the division of time is something like this. So I can multiply a scalar to a vector to construct another vector. So position vector, change in position vector, and then multiply a scalar. So, 1 over delta t is also scalar. So multiplying this scalar, I can construct another vector that is called velocity. And I can multiply mass in here, mass times velocity. What's that? That is a linear momentum. I would like to take the change in this momentum with respect to time. Then what I would get is mass times acceleration. In this manner, we can extend our understanding of nature from the beginning, this simple displacement vector, to arrive at velocity, acceleration, and then force, and further, and finally the energy or something like that. So if I write down some physical quantities, then that must have its role to understand the nature. So displacement multiplied by mass, or the displacement multiplied by mass, is the proportional to the linear momentum, something like that. So in this manner, I can multiply a scalar that is a real number and that can be separated into two pieces. This is called the distributive law. And we repeat the simple operation, multiplicative identity. If I multiply something, then the result is the same. Okay, that's multiplicative identity. If the result is the same after the addition, then it is additive identity. And if the result becomes the additive identity, then the operation is the sum with the additive inverse. If your result is returned to the 1, but in this case, there is no way to multiply, there is no multiplicative inverse in this case. Next, we consider two vectors x and y. We multiply a scalar, rescale a vector, elongate or shrink. So change the magnitude. Or sometimes if I multiply negative sign, change the direction from this to there, so negative sign, and then add them up. The solution of this equation that produces a zero vector is always a zero, and only this is the only solution for C1 and C2 makes the linear combination of x and y to be zero, then we would say they are linearly independent. It is actually trivial. In one dimension, there is no such vector. There is only a single vector. If there are two, they are always, for example, we have this vector and this vector, magnitude 1 and 1. So how can I have these two vectors. I want to multiply something, add them up to make a zero. Simple ways, put +1 in here, put -1 here. They cancel. Oh, this is +1 here, opposite. So +1 +1. This sum of this and this is always 0. Therefore, they are linearly dependent. They are linearly independent if and only if both of them must be 0. But both of them are non-zero. So in one dimension, there is only a single linearly independent vector. And actually, the number of linearly independent vector is called the mathematical dimension of vector space. So straight line, we have only a single And on the plane, we have two linearly independent vectors. And in three dimensions, there are three linearly independent vectors. The number of linearly independent vectors in a vector space is called the mathematical dimension of a vector space. Okay. Scalar product. In one dimension, scalar product is trivial. Multiplication of two numbers. Okay, so multiplication of two numbers. Multiplication of two numbers. I have x, y. If they are on the same side relative to the origin, then scalar product is just a product. If they are opposite side, one is a positive, the other is a negative. For example, a vector is always expressed as E1 and E1. This is called the completeness relation. Completeness relation. Complete, it means, it indicates that it doesn't miss anything. So any one-dimensional vector can be expressed as a linear combination of a single linearly independent vector that is called the basis vector. So anyway, in one dimension, scalar product is nothing but the product of the Cartesian component. This is called x, without both or without an arrow. Okay. And you know how to compute the absolute value of a real number, and actually that is the magnitude of a vector in one dimension. And in general, scalar product is just product of the magnitude and cosine theta, where theta is the angle between them, but angle is either parallel or anti-parallel. These values are either plus or minus. Plus, positive if they are on the same side relative to the origin, minus if they are on either one by one. One is greater than on the right side and the other is on the left side. So remaining part is very easy to understand. You can apply what you learn to the read it through for the remaining part. And if you have any question, you can always ask me. Okay, that's it for today.